Okay, well, it was good to get that working, better than speaking without any slides here. So my name is Dana Sorensen. I'm a graduate student at Utah State University. I'm here with Colton Lindstrom to present some research that we've done on an arbitrary bandwidth receiver architecture. So we're going to go over some of the motivation for this research, go over some of the simulations and the theory that we've developed for it, and then show off a little bit of a proof of concept that we worked on as well. So the motivation for this research actually came from the small satellite industry. I don't know how many of you have some experience in there, but these small satellites, these CubeSats, are about the size of a shoebox. So they're very small, they're very constrained on power and size requirements. So this presents an interesting challenge for radio communication interfaces. Because as the technology progresses, they're continuously generating more and more data, and they want to get more and more back to Earth. And in general, when you have a small, low data rate radio, you can do that with small and low power. But as you go higher and higher data rates, you tend to push over into large size, larger mass, and larger power requirements. And what we wanted to do, what our proposal was, take some of these really well-engineered, well-designed RFIC chips, such as the 9361, where there's been a lot of investment in this over the last decade from various industries and several companies even here at the conference, to produce these extremely tiny RFIC chips that have a lot of capability and a very low power consumption. So our idea here is to use multiple of these RFIC chips to essentially emulate a single wideband receiver. And just to clarify, I'm not talking about individual channels channelizing these receivers, but actually doing some data processing on these in real time on the receiver in order to have them act as a coherent single wideband receiver, and they'd be able to receive a large wideband signal across the bandwidth of all of the component RFICs. So this slide shows kind of some of the progression on some CubeSat missions in the last decade, how they've gone from single megabit per second, and they're kind of starting to push the limit up all the way to gigabits. This is enabled by, we're starting to use the Ka band on small satellites, where instead of having a couple megahertz, you've suddenly got 100 megahertz or even up to gigahertz of bandwidth to play with. An interesting note, of 750, 800 CubeSats, only about 35 of them are using data rates that exceed 1 megabit per second. So there's a lot of room for improvement here. So this is the concept in a little more detail. You have a single wideband signal that's too wide to be received with any single receiver. So the idea is to use multiple receivers, have each receiver receive just a portion of that bandwidth, and then do some processing to shape them and equalize them and synchronize them so that they can be recombined into a single signal. And again, this is because if you look out on the market at what kind of commercial off-the-shelf software-defined radios there are right now, it's hard to find anything past 100 megahertz bandwidth or 100 megahertz sample rate. You're going to really start paying for it if you want to push past those data rates. And most of them are around 60 even. So here's some of the theory behind it, some of the simulations that we did. Again, what we're trying to achieve is essentially get a single wideband receiver from multiple smaller receivers and some digital signal processing logic here. And this could be, it's not limited to 2. It could be any number of receivers, creating essentially an arbitrarily large bandwidth receiver. And this could also be turned around for the transmit side, which we'll talk about a little bit at the end. So the first thing, the first challenge is shaping the received signals. If you look here, if we receive individual signals from each receiver, each of those receivers has some associated filtering that it's doing. It's shaping the signal. Could be in hardware, could be even software filters. So if we just took the signals and added them together, they wouldn't really add together into the the single signal that we're trying to get to. You'd have a really bumpy frequency domain plot here. So fortunately, this is an easy problem to solve. Nyquist filters, which most of you are probably familiar with, are very common because of their zero ISI properties. An interesting side effect of the zero ISI property is that the frequency domain representation of these filters, when you position them just right apart, the transition region between the filters adds to a nice unity gain across the passband. So you can see we've got a red filter here, a blue filter here. You space them apart just right and add them together, and you get this green filter that acts as a single, nice, large filter. So that's great, and that's easy because Nyquist filters are common, they're very well understood, they're easy to design. Unfortunately, since usually what we're dealing with is complex IQ samples, magnitude is only half of the picture. We have phase as well. So this is what happens when you try to just take what we had in this previous slide on complex data and add it together. You have a blue filter, red filter, you add them together and you get this green one with a big dip in the middle where 0.5 plus 0.5 equals 0.6. And this is obviously a problem. If you tried to receive a signal like this, your eye diagram would look something like this. And that is an eye diagram. It's kind of hard to tell because there's so much distortion in it. So here on the right, we've plotted the magnitude and the phase of the filters. And this is an animation. We're going to sweep through the frequencies here. And you can see, as we sweep through, these two plots are the same. This one's just not spinning, so it's easier to see. The phase of the green filter starts at the phase or the angle of the blue one, as we see here when it repeats. And then it transitions over the transition region to the phase or the angle of the red one. And while it's transitioning, the magnitude there is not using the combined magnitude of the two filters because they're out of phase. So this is an issue. One way that we can solve this is just make it a filter design problem. How do we adjust the phases of those filters so that across the transition region they have the same phase, and we can avoid that. And that's fairly easy. We can do that. Just add a constant phase offset to each filter. And that works, as we see in this slide, where we've got the same filter's magnitude response, but with the phases slightly shifted so that as we sweep across the region here, as we go from the blue region to the red region, you can see a very nice even handoff between one filter and the other. So this works really well. It produces a nice clean eye diagram. You can get your signal. But it has a couple problems with it. One of those is, depending on your receiver architecture, the phase offsets might not be constant. If you don't have a shared local oscillator, if you're not using a coherent receivers, this isn't going to be the case. Depending on your receiver architecture, you could have PLLs in there that are locking onto a reference that's the same frequency but different phases, meaning every time you turn it on, that phase offset is different. You got to calibrate it again out of your system. So what we wanted to do is add some feedback, and that's what we did. So here we have, I'll switch to this side for you guys over there. We've got shaping filters. These are the Nyquist filters I talked about. The signals coming in. At this point in the chain, the signals are at baseband. So they need to be shifted apart so that they can be added together to produce the baseband signal of the wideband received signal that we're trying to get to. So then they go through a phase error detector. What this essentially does is it looks only at the transition region where some of the signal is shared between both of these chains, both these lines, and it detects the phase difference between the two. That drives a signal that's proportional to the phase error, which then goes through a loop filter, drives a synthesizer, which shifts the phases on these complex exponentials that are being used to shift the signal. And then finally, they're added together to produce the combined signal output. An interesting note is that this is essentially just a digital PLL that's been slightly modified to produce these shifting signals and to look at specifically the phase error in the transition region. So it's a fairly common or lightweight signal processing algorithm. So here's a animation of some of the, this was taken with real data from two 9361 receivers. We implemented the whole algorithm, simulated it in MATLAB. And you can see here, when we start out, it very quickly, within a couple milliseconds, locks onto the signal. You can see it, initially the I diagram is just a complete mess, but it very quickly sorts out those phases so that the signals are added coherently. And you can see that also in the bottom here, where the orange signal is the combined signal using no feedback. So you have that kind of characteristic dip in the middle from the phase not being synchronized. And then the blue signal starts out with the dip, but very quickly jumps up and has a nice uniform passband region there. And I don't know about you, but this is very satisfying to watch that lock on so quickly. Okay, so we didn't want to just make this be a theoretical project. We wanted to actually implement this in hardware. So that's what we did. We got some toys to play with. We used Analog Devices FM-Comms 5 board, which is really nice. It has two 9361 receivers on it. It's got a lot of options, more SMA ports than you'll probably ever use in your life. But each one of these receivers can receive up to about 56 megahertz, so 56 megasamples per second of data. And this card also has options for synchronized sample clocks between the receivers, and you can drive them with an external shared local oscillator, which in our case we elected not to use. This board is attached to just a Xilinx SOC dev board, which provided the FPGA and processing power for the implementation of the algorithm that I was just talking about. So this is what we used. We had a host PC running New Radio. We used a simple off-the-shelf webcam, grabbed some frames from that, modulated it out, sent it to a USRP that produced a single wideband signal. And then we had this FM-Comms board with two channels receiving that signal, pushing data onto the FPGA where it was processed using the signal synchronization that we were just talking about. And then we had the onboard processor on the Zinc FPGA actually running Linux with GNU Radio in order to receive that signal, demodulate it, and reform the camera frames that we were sending. So here's our GNU Radio flow graph. It's pretty standard. There's nothing fancy going on here. All of the signal combining is happening under the hood in the FPGA as it's received. There's a couple custom blocks here. Camera source here is just a wrapper to an OpenCV interface to a camera, pulling frames out. We modulate it, send it out. This FM-Comms 5 source is provided with the reference image with the board we were using, but it's been modified here. Normally you have two different channels here, independent channels. But what this is actually sending out is interleaved samples from the coherent wideband signal that's been reconstructed in the firmware. And the reason for that is because, of course, since you have double the bandwidth, you've got double the sample rate, twice as many samples. So the way we handled that was just interleaving those samples between two of the channels. So the first thing we do is de-interleave those, send them through some clock synchronization, timing, recovery, etc., demodulate, and pull the frames out and display them. So fairly simple. And in this, GNU Radio proved to be a really useful tool. We were pretty constrained on time and budget for this proof of concept. And so having the opportunity, the availability of GNU Radio to just drag and drop receive blocks and not having to build up an entire receiver architecture just for this proof of concept was really valuable for us. So here's a little screenshot of what we had in GNU Radio. This was in our real-time test, where you can see clearly we got the blue half of the signal, the red half of the signal, and they're added together into this nice green one, which you can see we've got definitely clear signal distinctions. so it's looking good. We also were able to look at this using the IO scope, which was, I think, mentioned earlier today in one of the talks. This allowed us to pull samples directly from the FPGA and watch them in real time. So you can see right half the signal, left half the signal. These are both at baseband, so they have to be shifted apart from each other before they're added. And then depending on whether the synchronization is turned on or off, if it's turned on, you get a nice, even passband across there. If it's off, you get that characteristic dip in there from the lack of phase synchronization. And one thing to note is that this phase offset here is not constant. What that means is that this dip is essentially just moving up and down continuously. You know, it essentially form a null, and then it would come back up, and then just go up and down, up and down. But with the phase synchronization turned on, we'd get a nice consistent signal. So after we implemented this, we wanted to characterize it and get an idea of the performance, you know, some of the implementation loss of this feedback loop in here. And we had kind of a serendipitous result here. If you notice, the blue curve is the theoretical QPSK bit error rate for an uncoded QPSK signal. And the orange one is our combined receivers. And you'll notice it's actually performing better than a single receiver would. And this is actually because in the overlapping region of the signal, you've got two components in each signal coming in, the signal and the noise. The signals are being added together coherently thanks to our synchronization logic, and the noise, of course, adds together incoherently. What that means is that you get an increased SNR in the transition region, and increased SNR in that portion of your signal, and that translates to actually a better bit error rate than you could achieve otherwise. And it was enough to actually overcome the implementation loss from the synchronization logic involved. So that was a serendipitous result that we didn't realize until we'd actually implemented it. So in conclusion, we were able to show that this is a feasible arbitrary bandwidth radio architecture. You could take as many receivers as you want. You're limited only by your processing power in the FPGA, which isn't a lot because it's a pretty simple algorithm. You can operate in real time, combine as many signals as you want, and receive arbitrary bandwidth signal. So we proved this on the RX side. On the TX side, it's essentially the same thing. One nice feature of the 9361s is there's an internal loopback that you can enable so that when you're transmitting, you can receive on one of the receive channels the same signal you're transmitting, and you could use that to synchronize the signals in the exact same way. There's a couple things you could do with this. If you were using shared local oscillator, so you had a coherent receivers, then you could use this feedback loop to essentially calibrate or find the right phase offsets and then turn that off. You'd save some power, and if they're using a coherent local oscillator, then they're not going to be drifting from each other. So there's a lot of options, a lot of things you could do with this. It's an exciting project to work on, and a good opportunity to get familiar with the new radio and many of the other tools that we used here. So, any questions?
So just to clarify your experimental setup, you're using the two channels in the ADI chip, or were there two different ADI chips for the two different receivers? And if so, did you have to do anything normalizing the noise floor, calibrating anything else? It was just the phase calibration, or were there other things that you had to do to manage those differences in the analog parts?
So if I understand the question is, did we do any calibration other than the phase synchronization, and how were we using the channels on the 9361s? Well, for the channels, each of the 9361s has two receive and two transmit channels. Unfortunately, they're locked to the same oscillator frequency, so you can't use them to receive two different frequency bands at once. So we used one channel from each of the chips, and then there was no synchronization on them other than the phase synchronization that we did with an adaptive feedback loop.
But they were close enough as far as the specs of the RF, like noise floor, other like IQ imbalance, that none of that really showed up in your measurements there?
Right, we didn't have to deal with that.
Extremely interesting, thank you. So the question I have is, you were talking about being satisfying to watch it converge, right?
Yeah.
Yeah. So did you test it against burst transmissions?
No, that's an interesting question. I'm glad you brought that up. So we just tested it using this continuous signal here. But that is an interesting point, because if there's no signal in the transition region, there's nothing to synchronize off of, right? So if you had a bursty kind of transmission here, you'd probably need some kind of tone transmitted in that transition region to calibrate off of, for a millisecond or two to let it lock on before you actually send your signal.
Hi, yeah, this might be a dumb question, but why in the transition region did you need to worry about combining and the phase? Why not just take one or the other?
That is a good question. The reason for this is because we want a nice, smooth transition region across the two. We don't want any discontinuities across that region. If you just use one, you're still going to have to cut off and switch to the other receiver at some point. And it's if you're familiar with signal processing filter design, it's really hard to design a filter that just cuts off immediately and then transition to another one. So I think even if we had only used one of the signals in the transition region, you'd still have to deal with a phase discontinuity when you jumped to the other receiver. So that answer your question?
Yeah, good answer, thanks.
My question is, what is the modulation techniques / waveforms?
Yeah, so in the proof of concept test we did, we just used exclusively QPSK waveform.
Yeah, this one I saw, but if this is your QPSK, you're dead. This one I can tell you, your error is incredibly big, and you will have problems. And the second one, did you consider the Doppler shift? Or this is just point-to-point static link?
That's a good question. We did not consider Doppler shift, which may cause some problems because it may change where your transition region lies. But that is a good topic, something that could be improved or further researched here. So thank you.
Maybe one more question, if there is one.
I think there's one over here.
Okay, if not, then we'll thank you one more time.
Thank you.